All right, recording is rolling. It is Wednesday, January 17th. I have a lab lined up for you guys today and tomorrow. Actually, decided to go ahead and do this one today because we got a slightly short schedule. I think it's a better fit. So speed of sound. I'm gonna have you guys calculate the speed of sound using PVC pipes and tuning forks. So I'll do a demo, show you guys how to do that. Some other stuff. Got a rocket launch after school, 5:11 p.m. They're sending 3 astronauts to the International Space Station. Want to catch that? Talk at 9. But before any of this stuff, it's also 3 last textbook puzzles we got to cover. And my last honors class, this was like the perfect fit, so this fit in perfectly. So last week I covered all the chapter 14 and most of the 15. We just got these last 3 to do. Actually, one of them is almost exactly today's lab. They just do it kind of reverse of what we're going to do in class. So this question and what we're actually going to do kind of reverse processes. So let's do these last 3. In fact, maybe I'll do these like reverse order, so it kind of leads into the one that looks a lot like today's lab. So number 93, guitar strings. Guitar strings says the equation needed for a speed of a wave on a string. And this one I did turn into a poster. And so there's the equation blowing up, boom, like that. Right. So speed of wave on a string. There's the tension of the string. Here's linear mass density. I went ahead and wrote that out as mass per unit length. Right. They use the character mu to represent that. Right. Here's the wave formula. Speed is wavelength times frequency. Right. So we're gonna make a connection here. The basic premise of this question is, if you want to target a certain musical note, how tight do you have to make the string? Right. So you're turning the tuning peg. You're trying to tune. Say a guitar string. Okay. So they gave some numbers here. They gave the mass of the string is so many grams. Now, guys, grams. I probably want to convert that to kilograms before I do any math with that, right? They gave the length of the string is 65 centimeters and want to convert that to, in this case, meters before you do any math with that. What should the tension be in the string to produce a note with a frequency of 147 hertz, right? It's going to correspond to some musical note. Right. So I'm gonna look that up real fast. All right. So according to Google, that is a D note. Right. It's 147 hertz we're aiming for. Okay. So, right. I'll get this on here, right, and then see what are our given values for this guitar string. We got. Right, I bet the guitar string is vibrating something about like this, like looking like that picture. It's right. So that right there is the length of the string. But remember that the full wavelength, guys, what is the full wavelength compared to what I just drew? Yeah, it's double, exactly. Yeah. Right. So there's the full wavelength. There's lambda. Right, lambda, right, which is actually 2 times the length of the string. Okay? Oh, the numbers they give us here said the mass of the string is 3.2 grams. Now I'm going to convert that from the get-go. Let's go 0.0032 kilograms. That's 3 decimal places. Okay. Would be kilo. 65 centimeters. So the length of the string, I'll call it 0.65 meters. And the target frequency, in this case a D note, is going to be 147 hertz. Okay. Right. So there you go. There's the given values right there. Givens. Right. We got to know is return the tuning peg. How tight do we make the string? So we're trying to target this tension right here. That's what we're doing. Okay. Oh, I bet we can follow this process pretty close right here, right? Like the wavelength would be double the length of the string itself. So we go to that. Right. So therefore, wavelength is 2L, which therefore equals. Let's go ahead and get a number there. Just be this times 2. Well, but 1.30 meters, I think. Is that right? 1.30 meters. Right. Boom. Okay. So now we got the wavelength. See, we know the target frequency. So speed is wavelength times frequency. It's just the associated speed on the string. So speed is wavelength times frequency. Right, let's call that 1.30 meters wavelength, and then 147 hertz frequency. Let's see, what is that? Right, I'm looking at 191 meters per second. Well, 191.1. Maybe I'll keep an extra decimal place. Right? Meters per second. Okay, that's what that would be. Okay. So we got that. Right. Now we need to tackle this top box right here. Okay. So speed is square root tension divided by linear mass density, which is mass per unit length. That right? Okay. And we know everything at this point except for this tension. Right? Just trying to solve. Okay. So we figured the speed of the wave on the string itself. Right. No, this is not the speed of sound. It's the speed of the wave on the string. Right? This is a standing wave. A weird concept. 191.1 meter per second is what we came up with. Right? Square root of the tension, the target tension divided by, we have linear mass density. So 0.0032 kilogram, 0.0032 kilogram mass divided by, and then the length of the string itself, remember, was 0.65 meters. So that's going to feed it right here. 0.65 meters. Right? That linear mass density has to do with how thick is the string, basically, right? Like if you look at guitar strings, there's thick ones, there's thin ones, right? I guess this would be the third thickest one. If we're targeting a D note, it's probably what that corresponds to. This is different ways to manufacture that. Okay, so algebra, got to square both sides. Let's take 191.1 meter per second. I'm gonna square that, right? It gives me this number, then multiply by this linear mass density, so times 0.0032 over 0.65, right? That'll give me the tension on the string. Okay, I'm looking at 180 newtons, 180 newtons right there. Okay. You guys good with that one? Okay. That was number 93, I think it was. It's the last one. Okay. You label that 93. There we go, 93. Okay. Next one, number 83. Oh, also musical instrument. I think it's fitting the three we're doing are all related to sound of music. Okay. Today's lab. One open organ pipe has a length of so many millimeters. A second pipe should have a pitch that is 1 major third higher. How long should the second pipe be? Right. So 83, imagine organ pipes. Maybe one organ pipe looks like this, right? And they told us a length of 836 millimeters, right? Maybe I should go ahead and convert that to meters, just to be safe. Why not? Although, gotta sort of solve those ratios anyway. But guys, is that called L equals 0.836 meters? Is what that would be, right? So that's a little bit less than a meter stick. So look at a meter stick. You guys can use later today, a little bit shorter than that, at 84 centimeters. Right? So if you blow some air through that, it's up a standing wave, we'll sound it out, right? Well, let's say, for example, it's like, right? And we're trying to hit the major third above that. So what's the major third interval set? It's probably pretty close to major third interval. Okay. Guys, if we're going higher musical note, should it be longer or shorter? How about a shorter pipe? Thinking like a shorter pipe, right? Okay. Maybe I'll call this L naught, and then I'll call this one, how about L3 for like the major third note? Right? So I've got L naught and L3. How about that? Okay. So how long does that have to be? Right? Now, got a poster that's going to help us out for this one too, right? Oh, and has the major third on it. Now, I don't have all the musical notes, but one of the ones I have happens to be the question, right? Major third, right? So in terms of frequency, that's what these are, right? These are frequency ratios. We're looking at a 5-to-4 ratio in terms of frequency, like the number of hertz, right? They asked about pipe length, right? Okay, so we have to go the extra step of speed is wavelength times frequency. This is what we have to do after that, right? But they actually have two different definitions that could result in two slightly different answers. And I want to do it both ways so we can compare the two answers, right? Because there's different ways to define intervals, right? I think I was calling this Pythagorean the other day. I double checked it though. I think it's more like just intonation or something. Pythagorean is slightly different. And this is equal temperament. So we'll do each way. And we'll see what we get. So let's start with the this 5-to-4 ratio. That's what we're looking at. So I know speed is equal to wavelength times frequency, right? And here's the speed of sound, because it would be a sound wave going through this pipe, right? Your guys' lab later today, it's going to similar setup to this one. You're going to use this later. Okay? And the wavelength, well, now I need to be thinking about pipes. So let me bring in my pipe poster, your pipe poster. I'm going to say an organ, well, okay. I'm going to assume the organ pipe looks some version of this. Maybe there's some vibration here, like a high pressure point and something, right? Even if I pick the wrong type pipe, in terms of the ratios, I'll still get the right answer at the end. But I'm going to assume this, okay? So let's say if this is true, guys, how many wavelengths is this right here? Is that a quarter of a wavelength, right? So you got 1/4, 2/4, 3/4. This guy's 3/4, right? Oh, and it says right here, 1/4 wavelength, 3/4 wavelength. Okay, okay, for this type pipe. Okay. Again, if I pick the wrong model in terms of the ratios, I'll still get the right answer at the end. Okay? So assuming that model though, this right here would be this wavelength would be 4 times the length of the pipe, right? That'll end up canceling out at the end, but whatever. Right, so speed of sound is 4 times the length of the pipe times the target frequency. Okay, I'll call this L naught and frequency naught. So that, okay. Right, so there's the original setup. Right, now that's for this first pipe. That's like for the root note. We play the original note. Now we need to play the major third above that. Right. Ooh, guys, is it gonna be the same speed? Like if I talk in a low voice or a high voice? Does all those sounds travel the same speed? Yeah, they're all the same speed. They're all the speed of sound. But they're a little subscript, maybe speed of sound. Speed of sound equals, right? But now we need some new length, right? Now, in terms of the wavelength, it'll still be 4 times whatever, right? This could be some new pipe length, right? And then times the new frequency above that. Now, here's where I can make the substitution, right? Well, I'll do it this way. I'll call it F sub 3, right? And then I'll save the substitution for later, right? Because here's my system of equations, sort of, right? System, right? I'm comparing these 2 pipes, right? And they have some things in common, right? Like they have this, the speed of sound is the same for both. This factor 4 is just going to cancel out immediately, right? But there's 2 different lengths and 2 different frequencies associated, right? So maybe I could like divide these 2. This is just one approach. It's just one math approach. See, the advantage of doing it this way is that all the commonalities immediately cancel out. V over V is just 1, 4 over 4 goes away. And then the ratio of the lengths of the pipe times ratio of frequencies, right? This all equals 1. So I can do a little cross multiplication. I'm trying to target what is L3. That's the ultimate question. So maybe I should cross multiply that up. Is that true? I'm gonna get the target length is equal to the length of the original pipe times the ratio of the frequencies, right? In this particular order, right? So here's a good general answer in terms of variables. I haven't actually plugged in the any numbers yet, right? But I can do that here. Let's do 2 different approaches. Well, I'm going to split the paper and do 2 different approaches from this point. Get 2 slightly different answers. Okay? I'll call one approach Pythagorean. Although I don't know if that's exactly right, but I'll call it that. Right? I'll call the other one equal temperament. Equal temperament. All right, let's see what we get. Okay. So L3 equals, right? Now the original length is the same regardless, which is the 836 millimeters, so 0.836 meters. Right? I guess if you never convert it, it wouldn't matter because this is a ratio answer now, right? Times the root note frequency, also same for both. They said oh, no, sorry, they never told us the frequency. We were just looking for ratios, so I'll just call it F naught. Right? We don't even know what the root note is. Okay? And then the major third above that. Now, if I'm using this particular method, I care about ratios. It's a 5-to-4 ratio. So this is the major third is 5/4 times the original, right? And you guys see whatever the root note was cancels out, right? And I'm gonna take, guys, what's 1 divided by 5/4? Is that the same thing as multiplying by 4/5? Right, multiply by 4/5. So I take my 836 millimeters and multiply by 4/5, right? So there's a lot of math to get that point, but you guys sort of see the shortcut to the answer. It's just like the reverse of this. That's why this in terms of length, right? So I'm getting 0.669 meters, right? That's using that ratio method that I'm calling Pythagorean. Okay? Now the equal temperament uses this log scale or exponents, if you like. Right? It's the flip side of that, right? So it's something to do with this, right? So what is the target note compared to the root note? It says 2 to the power of the number of half steps divided by 12. Right? Now, the major third is like 4 half steps above the root. Like if you count like piano keys or so 4. So I'm going to plug in a 4 where that n is 4. So I'll say the target frequency is equal to the root frequency times 2 to the power of, in this case, 4 over 12. Okay, see what I get out of that. What is 2 to the 4 out of 12? 2 to the 4 on 12, right, is 1.2599. Right, so if I do the same thing, right, the target length is the original length times, okay, use this model right here. This is 1.2599 F naught, right? The F naught again cancels out, right? Right, that divided by that, right? So 0.836 divided by answer is, right, length 3, 0.664 meters, right? There we go. So we set up a system and did a little bit of algebra in terms of variables to get a framework, right? And we said, well, okay, there's a little different definitions how you could tune things. So I picked 2, tried it out, you get slightly different answers, right? So there you go. Right? I think according to what I read, the one on the left actually sounds a little bit better in your ear, right? But modern day instruments are probably tuned according to the one on the right. Spanish, you can switch keys and it all sounds sort of the same, right? And one last one, which I told you guys is going to be real similar to today's lab. Number 71, a vertical tube with a tap at the base filled with water, and a tuning fork vibrates over the mouth. And as the water level is lowered in the tube, resonance is heard at the 17 centimeter level and at the 49 centimeter level. What's the frequency of the tuning fork, right? Yeah, this is exactly backwards of today's lab, right? See, I have a tuning fork here that has the frequency stamped in it. So we're going to start by knowing that value and have you guys calculate the speed of sound. Here, we'll do the whole thing backwards. So 71, okay? And the poster I have for this one, here, this right here. Okay. So they said it's going to resonate at 17 centimeters and also at 49 centimeters. I'll demo those for you guys in a few minutes too. Okay. And so and the advantage of having the water level is that it closes off one end, right? So we're going to do, instead of letting the water drain, we're going to lift and lower the pipe, right? So it would sound like this. If you strike the tuning fork, someplace it's going to resonate. So it's like, and then that's where you set up a standing wave, right? So like approximately a quarter wavelength, approximately 3/4 wavelength, right? Those aren't exact, but if you take the difference, that should be real close to exactly half a wavelength, because these waves actually, the low pressure point is actually a little bit above the pipe, so that aside, right? I'm going to say if L1 and L2 was it 0.17 meters and 0.49 meters, right? That difference is that 2, 3, that many meters, I think, right? And that would represent half of a wavelength, right? About 3/4 wavelength minus about a quarter wavelength. Wouldn't it be half a wavelength? Right? So this right here is half of a wavelength. Right? So double that, and you get the full wavelength. So the full wavelength is 0.64 meters. Right? Right. Now let's go to the wave equation. It says speed is equal to wavelength times frequency. Well, here's your wavelength. And the speed, well, we're going to assume something that would be reasonable, right? Does anybody remember from last few days what's a good round number for speed of sound? Say room temperature, 1 Earth atmosphere. What's the speed of sound from my voice to your ears? Yeah, let's call it about 340 meters per second, right? It's slightly different textbook values, probably be different in Denver, Colorado, probably different in the summer than the winter, but that's probably it. So 340 meters per second is 0.64 meters wavelength times the frequency on the tuning fork. Divide that, it's 340 over 0.64. Okay. Looking at frequency is 531 hertz. 531 hertz, right there. Right. Ooh, you know what? This tuning fork I happen to have in front of me is 512 hertz. That's okay, not the same musical note, but it's not too far off. What does it sound like? kind of hard here. Can you guys see that? Yeah, there you go. All right. All right. So you guys good with the textbook puzzles? Yeah. And so let's have those due Friday. If you need to go take another look at those, I'll get you guys your quiz soon too. I don't have it printed exactly right now, but pretty soon. Okay, so that covers all textbook puzzles. Let's switch over to this lab.